Welcome on the session how to load up the submodel in IDEA StatiCa Detail 2D. My name is Lukas and I work as a computational validation engineer in company IDEA StatiCa, and I will guide you through this session. So just briefly about the content, we'll talk about the global model for statically determinate structure, something about the equilibrium on the trimmed ends of the submodels, and principally key takeaways that will give you some summary and the overview. What are the important highlights of those sessions? So I utilized the power of the global model from I used Midas Civil X. As you can see, there is just the total length is 10 meters. The section 25 times 120 centimeters, like a section, and concrete C30/37. So I utilized the option to apply the uniform load. This is just one single load case, and based on you're able to also take pen and paper and calculate it by hand, but I wanted to demonstrate how does it look also with the numbers in every part of the shear force and the bending moment location. So those are the values, and our goal is to create in IDEA StatiCa Detail the trimmed part, or basically submodel, with the opening in the middle that will be reinforced, and to properly assign the end forces um, from the shear force, bending moment, and once you have normal force, there will be also the normal force. But in our case, this is just a simply supported beam with the zero level of the normal force. There are some essential and important prerequisites that you need to like um, take into account actually. And one of them, because we are solving the static like a statical structure, or structure that is basically static. There are no dynamic forces, and the structure need to stay on the place. So there need to be something what is called like a static equilibrium. So it means that forces and the moments must be satisfying the conditions that some of the forces in all directions has to be equal to zero, and some of the forces in or some of the moments have to be also equal to zero to having like model on the one place, not in the motion. There is important part that boundary internal forces from the global model must be applied to the submodel together with the member loads. This is, I think, this is the most important part that you should like take away, that once you create this trimmed part with the shear forces, those are some normal forces once they exist, and here are the bending moments that will basically sagging the beam at this direction. I mean, they are just bending up the model to like that. This is my positive direction of the bending moments, and there is important part that all of the loads that exist on the submodel need to be um, applied together with the internal forces at the trimmed ends. So for nonlinear analysis, the member forces um, applied must be basically applied and transferred to the submodel, also with the loads as I mentioned, and we are taking the advantage of the forces, because for nonlinear simulations, the stiffness is changing, so there is highly recommended to utilize forces rather than the displacements for stress redistribution. And this is what we actually have in the IDEA StatiCa 2D detail. But if you want to load it up the model, we are taking over the forces from the 1D beam element to like a 2D wall. So you need to somehow apply and redistribute the nodal forces into the wall. So we are utilizing the power of Saint-Venant zone that is running out of the calculation, and there are like off results at this part. This part is basically rigid, and the nodal forces like here is a x, here is a z, and here is the y, because this is as I mentioned, it's a 2D plane stress task, what we support in the 2D detail, and there are some links. There's some constraints or rigid interpolations that we use, or that we call rigid body equation 2. Maybe you know it from the abacus or ANSYS. It's providing you the I would say rigid body behavior. So once you apply, for example, the bending moment, what will happen? Actually, that this part will be rotated as like that. This point is staying in the center of the gravity of the section. So this is my rotation. Okay, and also the shear forces are basically applied equally at the end of the trim zone. So those part, or the descent when on zone part, is not analyzed, but the part beyond this threshold will be analyzed, but at this part will be properly redistributed the 1D internal forces into the 2D wall. So this is the goal, that you will not receive any like stress concentration or some artificial peaks on the model itself. This is highly beneficial and highly accurate approach for the distribution of the 1D forces. Okay, so let's go ahead to the how does it work. We will do two models. One is the entire beam to compare the results with the submodel. Actually, you're able to see that I just reinforced the part, put some opening, and also reinforced the area around the opening to capture the stress concentrations around that. And the most submitted part from the point of view of the tension is the reinforcement close to the bottom part of the opening, 437 megapascal, and under compression minus 91 megapascal for reinforcement bars. And as we can see, so if I just draw the plane of the strain, so you're able to see this is my plane of the strain. Here is the compression, and here is the tension. And because we support the diagram that basically you know exactly from the code, from the Eurocode, here is the sigma and here is the epsilon. So this is the level, because we are on the 10 megapascal, so maybe we are still on the like a linear part. So I will just put it here. Apology. Just take a different color. Yeah, so this will be basically under compression. There's like a 10 megapascal. I'm not right now. I don't know right now. The threshold will be like a 20 megapascal here. The design here is a 10, so we can consider that here will be still like a linear assumption, of the distribution of the stresses, and all the forces that are under tension, that are coming from the strain here, will be going to reinforcement bars. So what you're able to see here is a tension, and sorry, here's a compression, and here is a tension on the bars. And what about the submodel? Once we are just taking the advantage of the submodel, that you know why we are in general creating the submodels, because we have like a big structure and we want to simplify or more, or for example more refine the area and know the stress gradients, and being basically more precise, but also save the time for the calculation. So this is the reason why we just taking the advantage of the submodels. And once I will compare the results, you're able to see 98, 438 under tension, and 10.9 megapascal under compression. So actually, right now there is a space for demonstration how to do it, how to properly load it up, the submodel itself. I will start from the exactly from the scratch to show you how to take the advantage of the linear model that you already have in your global FEA and create the submodel if you know all the internal forces and the loads that is applied on the model. So I will open the IDEA StatiCa Detail. You can see that I'm able to take the advantage also of the 3D, but this is another story. Um, I will start from the scratch to show you how it works. You will select or pre-select the concrete grade, reinforcement bars. If you have some pre-stressing, maybe later on, but this is enough. And Eurocode as the desired code. So I will create the model, and I have like a blank project. So I will utilize the option for a beam and create the rectangular section. So the height is like a 1,200 millimeters, 250 millimeters is a width. Okay, once I have it, I can just move on and select the length. The total length will be like a 5 meters, and I know that my part will be trimmed at the ends, so trimmed on the both sides. So you'll be receiving some label or mark that identify and indicate that this part is trimmed. So only this part will be analyzed. The part that is basically behind the black line, that is measured as I would say, equal of the height of the section, will be of the analysis. Okay, so what you need to do, you need to put just the opening. The opening will be circular and will have diameter 0.7. So actually this is everything what I need. And right now I will put some reinforcement bars. I need some group of the bars, and the group of the bars, to properly align it, I will just rotate it in the 3D. My bars will have like a 16 millimeter diameter. There will be my cover will be like a 40 millimeters, and there will not be 3 bars in a layer. There will be just 2 bars in the layer, and let's have like a 6 number of the layers after 220, I do believe. Yeah, it looks quite symmetrical, 220, and I know that my bars are coming into the or continuously going to the beam. So those type of the restraint will help you to basically fix or constrain the reinforcement 3 bars at the end of the trimmed part. So that's perfectly anchored right now, and I will use the option to create another set of the bars that will be stirrups. the stirrups will have diameter 12. And if I double check how does it look in the 2D space, you can see that the stirrups will be after 300 millimeters. So I know that, for example, my first distance is 50 millimeters, and the rest is after 300 millimeters. So I would like to have it the distance or the stirrups directly in the middle. So I will put there 85. Maybe 95 to have it like properly aligned in the middle. Perfect. We have it. I will just save it somewhere. Okay. It sounds or it looks reasonably reinforced. I can see the bar is here. Everything is properly set up, and I will just put the cage around the opening. So another entity or template that will just identify the opening. So if I double check it in the 3D, you can see there are just the two layers that I would like to change the anchorage shape at the end and at the beginning. And basically, this is my reinforcement layout with diameter, for example, 8. And the anchorage length 250. So once I have it, I can proceed to the calculation. So in the check, I can just immediately run the calculation, but there are missing the loads. The most important part is as a load. So in the first case, I need to create properly the load case and put on the top the load of the 25 kilonewton per meter. So I need to go here and select the line load minus 25 kilonewton per meter. As you can see, once you set up the load, here is, of course, the model is not flying in the space. So it needs to be somewhere anchored, and here is the support actually at the end. So this is the reason why you need to have like a properly defined equilibrium, because it's like anchored somewhere in the space. And if you put the force, you're able to see it like a behave as a console. Yeah, so great. Right now, as I know that it works like that the support is basically here, I'm able to modify the section of my diagram. What I need to have like at the end of the trimmed end 62.5 kilonewton, and the bending moment at the trimmed end 234, in the middle 312. So I can take advantage to assign the bending moments and the shear force directly in the section of like directly to the section in the middle, because you're able to utilize every like a section wherever you want, but make it simple. Yeah, make it simple for you that you will assign where you will apply the load. So I know that my load will be applied in the 2.5 meters from the beginning. So you can see that here is I just received the 62.5 and minus 62.5. So what I need to do, I need to assign what will be the level of the internal forces directly at this section, or this trimmed part, or not trimmed part, but this position in the middle. So I know that my bending moment is 312.5. So once I know that, you can see automatically like recalculate the other internal forces that are existing on this trimmed part. So I have a 62.5, I have a 234.4, and this is exactly the same what is in your global model. So that's guarantee you that everything has been like a properly assigned, and you can move on. Once I want to move on, but I'm not able to do that because IDEA StatiCa Detail works with the combinations. So I just assign the combination with partial factors 1, and I'm able to right now analyze it for ultimate limit states. Of course, if you need, just assign service level limit states. So once you run it, you would be able to see the results quite swiftly. Okay, that's running. Great. So you can see there is like a 58% of the utilization on the concrete and 94.5% utilization on the reinforcement bars. So let's go double check what happened actually. As you can see, this is everything is under equilibrium. That's great. So, and I want to see the stress. The stress is 11.6. 11.6 megapascal. 11.6. So I can see that. I don't know. Yeah, okay, I see. There is no bar. You can see that the bar is not in there, or I'm not able to see that. Yeah, she's not there. So I need to put there like a 210 maybe, and put there like a higher. Just give me the sec. 220 is correct. 220 is correct. The 40 millimeters is also correct. Okay, so I will just turn off the stirrups and put there another type of the reinforcement. I will put there the group of the bars that will be on the right part. The diameter will be 12, and there will be like a 300 millimeters, 17 bars, and I will use this perfect anchorage. This is the equivalent to the stirrup. So it will look like that. You can see, but it will enable you to put there the top layer of the reinforcement bars. Perfect. So actually, it works well. I can just run it and see the results. It will lead to the like a decreasing of the stress in the compression. Why? Because the reinforcement bars with the portion of the stiffness of the bar will absorb some level of the compression. So you can see always you need to make some sanity check. But when something is not aligned according to your expectation, always double check your model. Okay, great. Perfect. We have like a 56 percent. You can just go in there and okay, it's not centered. It's not centered as I want. Maybe I will just shift it one more time, the bars, to have it like in the middle, because there will be like 85. Right now I'm in the middle. Perfect. Okay, this is my last calculation. Okay, perfect. So I'm exactly on the values that I want to be. So let's double check what is the stress. The stress level, I will just put it on the side. Sorry, I'll just put it on the side like that. I will show you the results from the whole beam. So we are able to double check what is happening. So what stress we received? As you can see on the submodel, we received 10.9 megapascal, 10.2, almost equivalent. From the point of view of the stresses on the reinforcement bars, I can just go here, see the stresses, and I will be able to see 98, 437, 437 is exactly the same value on the left side. That is a little bit higher values under compression. So we can say that the models are, I would say, equivalent once you go to the deflections. You're able to see, you can say, hey, it's a weird shape of the deformation, but you need to remember that some part of the member is like a fixed, so you it's like a you need to have like a perspective that you rotate it, and once you rotate it, you will exactly like a receive the shape of the shape of the deflection as you want, as is like a standard for the whole beam. Yeah. So you can see this is my deflections, 19.6, and here is like a 18.1. So a little bit small discrepancies in the results, but still for the submodel it behaves according to my expectation while you like spin it around, you know. Okay, so I do believe that that's all how to properly load it up the model. So let me come back to presentation to like sum it up some key takeaways. From my perspective, the main key takeaways for structural engineers is that the internal forces and the applied loads at the trimmed ends must be included in the submodel to preserve static equilibrium with the global that is like existing also in the global structure, you know. To have like a proper distribution of the stresses as in your global model as in your submodel. So it needs to be like a balanced, and based on that, when it's balanced, once the equilibrium exists, so you will get the consistent results. So because the global model is statically determinate and its boundary forces transfers directly and ambiguously to the nonlinear submodel, delivering a reliable and a physical correct model. It works for statically determinate structures. So actually, once you wanted to consult something or have a training for IDEA StatiCa, so do not hesitate and contact me, because I've been endorsed as the certified trainer of IDEA StatiCa. So you can just drop the message on the Struck Inside at gmail.com. So this is my social where I'm just posting posting some interesting stuff for structure engineers that are coming from the IDEA StatiCa, what we are preparing, what we are developing. So if you want to follow me on the socials, and as I mentioned, we were talking how to create a submodel from the statically determinate structure, but there it's completely different story once you have like a hyperstatic structure. So next session will be focused on the hyperstatic structures and the submodels in the IDEA StatiCa. So thank you for the attention, and have a nice day.